Dr. Rahman, I think now it will work.
Yeah, now I think it's open.
Very good, very good, very good.
I couldn't open it earlier.
Welcome.
Thank you very much. Thank you very much. So I would like to introduce you first. So I will take for a few seconds the screen, if you allowed me.
Yes, go ahead.
So you see, I guess, the screen. Ustad Salim?
Yes, it is clear. Yes, it is there.
It's working.
Yes, go ahead.
First of all, I would like to thank Professor Rahman. I know him, I think, 1 year ago when he contacted me for a European project, which I don't know if it's work, but anyway, I tried to contact Irizen to have some consortium for this project, and I saw how he's working very hard for this project, and I want to thank him also that he accept before when we have organized a conference in Wijda. He was there through the online, and now I asked him, and he immediately accepted. Professor Rahman, he received his bachelor and his master's degree in electrical engineering with distinction from Bangladesh University of Engineering and Technology. It's at Dhaka. I hope I made it correctly. In 1977 and in 1979, respectively. He also received 2 gold medals for being the best undergraduate and graduate student of the whole university in 76 and 79, respectively. In 79, he was awarded a Commonwealth scholarship to study for his PhD degree in UK. And 1982, he received his PhD degree in electronic engineering, I guess, from University College of London. In 1988, he joined City University of London as a lecturer, where he became a full professor in 2000 at City University. He led the research group on photonic modeling, specialized in the development of and use of rigorous and full vectorial numerical approach to design, analyze, and optimize a wide range of photonic devices. It's a huge work and a huge topic. He has published more than 650 journal and conference paper. In his journal paper have been cited more than 9,000 times, which each index over 43. He has supervised 34 students to complete the PhD degrees as their first supervisor and received more than 13 million pounds in research grant. Professor Rahman is Life Fellow of the AEEE and Fellow of the Optical Society of America and the SPI. I want to thank him for accepting to be with us. I think we will learn a lot from him in photonics. Photonics is a huge topic, which is very important for the future. And I want to let him, to give him the floor, the virtual floor. And I would like that they give him enough time to talk about his topic, and we will have some questions at the end before
Thanks, Dr. Ahmed. Thanks for your kind invitation. I think I need to share the screen. You please, Salim Omar, help me because my screen is at the back. And how we can you see the screen?
You can share your screen.
You can see that screen?
Still not. Open the presentation first, then make the share screen.
Presentation. It wants to share screen on this presentation.
No, you have to see the downstairs. you have part you can
Okay, share screen. There's a share screen.
Yes.
Yeah. Okay.
Yeah.
And again. Yeah.
Can you see now?
It is starting. Yes.
Now it's fine.
And maximize the.
Yeah, that will do. I'll do the slideshow now.
Yes.
Is
Yes.
it okay?
Very good. Very good.
Very good.
Okay. So first, thanks to Dr. Ahmed for inviting me to give me the opportunity to talk about photonics, and particularly I'll try to focus in new areas where all of us we need to work is called sustainable development goals. So the outline of my talk, I'll talk about briefly the photonics and how it reached the maturity, but the challenges of United Nations and other on global warming, or sometimes called sustainable development goal. What are the challenges we are facing? And photonics, a key technology, rather key enabling technology, how we can contribute towards that. And then I'll draw the conclusion. So basically, first, probably all of you know photonics, but if somebody you don't know photonics, it is like electronics manipulates electron, but photonics manipulate photons or light. So all the electronics related to the light or photon is photonics. How did it start? It started with the invention of semiconductor lasers and optical fibers. Both happened in 1960s, and they were both recognized with the Nobel Prizes. One of the work, optical fiber, it was in North London at Standard Telecommunication Lab by Cow and Hockham. They presented IEEE papers, and that becomes one of the main paper. And what they identified is that loss in the fiber, how it can be reduced. And the Corning in USA did reduce the loss. And Cow was recognized for his work by Nobel Prize. So one thing is that photonics is a technology which has been started with the development of mostly in telecommunication sector. Today, whatever you can see communication area is mostly dependent on the photonics. However, the money comes from not from telecommunication that much. More money comes from the consumer's product, and I'll try to brief on that. What is that? So first thing is the communication. As you can see, optical fiber is linking all the countries, all the major cities, and everywhere, whenever you think of your data, today I'm talking from here, and this slide, this data is going to your place, and it must be going through some sort of optical fiber. All the data transmission is through optical fiber. A single fiber can transfer more than terabits per second. But we are asking for more and more data, more and more faster data. There are 4.5 billion internet users in 2019. And the data rate is also increasing, the traffic. And you can see that is increasing 26% annual growth. And so the photonics technology has the responsibility to provide this data rate. And for that, the data rate every 10 years, increasing every 4 years is increasing 10 times. And you can see that over the year in the 80s, improved fiber, then came in EDFA, WDM, and more or less now these days, people are working on is space division multiplexing, that area. However, as my focus today is more on sustainable development goal than the communication. So briefly, the data demand is increasing. In 80s, WDM and EDFA helped, then came polarization division multiplexing. People are now working on space division multiplexing, mode division multiplexing, and also having a faster modulation and data. So the impact of photonics has been initially telecommunication. However, the appliances we can see every day, CD, DVD, display, scanner, printer, illumination, these are all comes from photonics. It has a large application in material processing, industrial processing, medical application, and also sensing. Briefly, if I tell, this was the data used to store, a music used to store for 3 minutes in a 78 RPM gramophone. Today, you store millions of songs or videos or films on a CD or DVD. Earlier generations, some of you might have seen, the TV was like that, a big cathode ray tube, but now it's a flat screen. And that is also because of the photonics, because the LED is the main driver. Printer, if you remember earlier, you used to print. If you want to have to multiple print, you might use a carbon underneath it, but now you can print color copies, multiple copies in a second. Healthcare, major operation, not only the eye surgeon, many major surgery, many imaging through the body, through your intestine is going through the fiber. Simple laser surgeries are for lots of cosmetic surgeries are there. Photonics is for illumination. Now, traditionally, most of the light is coming from LED, and I'll talk about that in a minute. Optical sensor is a massive market. There can be 200 sensors in a car, and many of them are optical sensors. Laser has an enormous sort of power density, and that's why it can do the material processing. It can cut enormous amount of metal thickness with extremely micron precision. And so when you're thinking of buying a Mercedes car, buying a BMW car, or a plane, most of these parts are now cut by laser. So this is the use of laser, but also when you think a little stent through your artery to help you from your cholesterol level or heart attack, this stent is also made by laser. So the rapid development of photonics during the Horizon 2020, EU research program spent 79 billion euros investment. And that time, photonics was identified as one of the 6 key enabling technology which can shape the technology landscape of this century. In the new research program, Horizon Europe has been launched. It started this autumn with a budget of 100 billion euros. It is focusing on technology, but technology which is green, technology which tackles global warming, technology which tackles the climate change, and focusing same way those sustainable development goals. So the Horizon Europe, 100 billion, we are developing the technology, but always in our mind that this green technology or environment. I have been working on photonics for more than 40 years. I've developed computationally efficient finite element method for photonics. I was first in the world to develop the vector H-field formulation, and this is being used in all the commercial and other codes. So initially, my focus has been more to support communication sectors. Last 10 years, I've been doing some work on optical sensing. But last few years, I'm exploring more and more on SDG, Sustainable Development Goal. So our work on Sustainable Development Goal is limited, but I will tell you what are the things possible. So what is photonics? As I said, it is a key enabling technology. It provides the background for communication technology, mobile phone, internet, 5G, 6G will be coming. All the communication as they're talking through the internet today and other day, all going through the optical fiber. But as I mentioned, it also produces the product of laser printer, LED screen, and also the LED lights. But what happens, this rapid growth of technology, we demand more and more speed in computer. We demand more and more internet data. That is also consuming the energy. And that can be responsible for global warming. So we need to think that we have to keep on developing, but also it has to be sustainable. So the global warming is coming because we are consuming more and more energy to keep the civilization going, keep the factories running, keep the car or the planes running, moving transport, the ships, have electricity in industry, to run the industry, also at home to run lights and all the equipments we have running with electricity. But over the many decades, these have produced and still producing carbon dioxide and a greenhouse gas, and that is the cause of global warming. And global temperature is keep on increasing slowly. So that global warming is causing the long drought, lack of water, lack of food, agriculture, but suddenly unprecedented heavy rain, so much raining that causing the flooding. There are frequently, you can hear about the hurricane. Hurricane has been there for thousands of years, but recently they're recurring more. Forest fire, you can hear every day or so in USA, in Australia, the forest fire. You hear the melting of the ice caps in the pole. And as their ice caps are melting, temperatures are rising in the sea, and also the sea level is rising. There are many countries in the world, like Bangladesh and other, they are just barely above the sea level. And even a 1 meter of sea level rise will flood a large part of many of these low-lying countries. So we have to be called sustainable development. We need to keep the civilization going, but without producing any net greenhouse gas. Only that way we can sustain the human existence without destroying the world. And that is the aim of United Nations Sustainable Development Goals. There are 17 Sustainable Development Goals has been identified. These are among them is a poverty, no hunger, good health, quality of education, gender equality. 6 is a clean water and sanitation. 7 is the affordable and clean energy, decent work, and also the climate action, better water, and health, all of them. So we are trying to see lots of people all over the world are working on many areas. We have only small input for last few years, and we want to focus on that. So there are 130 countries have pledged to the Paris Agreement, and the objective is that by 2050, the net carbon generation should be 0. That is a big challenge. This month, all the global leaders are coming to Glasgow, United Kingdom, to discuss their common commitment to fight global warming for the 0 carbon commitment they are meeting. So now let's look at the energy. We need energy. Always we need it, we will be needing it. What is the primary source? It has been the fossil fuel, coal, oil, natural gas. These are formed over billions of years. And the primary source has always been the sunlight. Sun is responsible for the growth of the plant. Plant grows and you get later on coal from there. Animals lives on plants, eating the plants, herbivorous plant. And then other animal, carnivorous, they're eating on those smaller elements. And from that, when they die, billions of fish or animals, you get oil, natural gas. So these has been produced over billions of years. And last few decades, we have been burning this fossil fuel. We started burning more rapidly without realizing the global warming. People are now aware. We wanted to slow it down, but we need the energy for industries, transport. We need that. So we have to think that how we can still get the energy without increasing the global world temperature. But remember, most of the renewable energy, we'll talk about that solar, wind, tidal, even hydroelectric, they are origin from the sun. Sun heating, another thing, cloud and everything gives the wind and tidal everything, except nuclear. It can give you electricity without producing carbon dioxide, but you will be end with spent fuel of uranium. They may last millions of years. And question is that how do you dispose those uranium? So the safer energy, renewable, can be from the top few. So sun is the all source of energy, as you know, including fossil, hydro, wind. But we can convert solar energy directly. And that is the primary goal. Everybody's trying to do that. Silicon solar cell is the dominant technology. Its efficiency is limiting, is coming to the limit. Even 5% increase of the efficiency by using sort of multi-junction, tandem, many other tricks. If we can increase even 5% efficiency, that will be enough energy to supply many, many smaller countries. And as you can see from the graph, that this is the brown one is the coal, and we are reducing the coal use less. gas and others is still increasing, but solar power is increasing much rapidly. And that is we expect, and because the price of solar cell is coming down rapidly, and now solar cell is the cheapest renewable energy. Not only that, if the oil and petrol price goes up, as it has gone up double in last 1 year, solar energy can be cheapest of all the sources, and which is also green. So you can see that there are lots of solar cell developed all over the world. Now we are lucky, and you can see that Morocco has been lucky, and many African countries near the equator, God has blessed us with a strong sunshine, so we can utilize this solar energy. But what we're doing today, if you look at it, most of the solar energy, here you have the dominant solar energy, but not many countries are producing lots of solar energy for their consumption. Morocco still is doing good, and obviously great good to Ahmed and other groups there. So what we need is that we need to, so the previous slide is showing that although the solar energy is higher in Africa, but the solar energy consumption in Africa is less. That is only because the solar cell price is affordable for the West, but not so yet affordable for the developing countries. So we need to reduce the solar cell price further so that many poor developing countries can take more and more use of more and more solar cell. And that responsibility lies with Photonics. Dr. Ahmed is an expert on solar cell. He has been working on that. And also we heard from IRSN CEO about their work on solar energy. So is that not only we are maybe a small player, but all over the world, lots of groups are working to improve the solar energy. But I'll talk about that. Besides that, there are other things also we need. And tomorrow, Khaja Naziruddin will talk about perovskite cell. It has a nice advantage. It is much cheaper than silicon and also flexible. And being flexible, it is very easy to install. It won't, like crystalline silicon, it won't crack or damage that easily. So it is cheaper and flexible, easy to install also, cheaper to install. Efficiency is getting better, is nearly of that of silicon solar cell. But problem still with the perovskite is operating life is shorter. It also contains some lead. So lead is a toxic. So there are many, many groups all over the world are working how to make their life longer, how to reduce the toxicity by reducing lead or replacing the lead, and also how to make them even the price, because you can use inkjet printing technique to reduce the price. And those are the people like Khaja and Ahmed are working to make better solar cell, cheaper solar cell. Our work is very, very limited. As I said, we only started working in last 1 or 2 years. So last year we published in Optics Express saying that in a silicon solar cell, you can use the nano pillar and also different sort of design to improve the efficiency. We are looking at a nano pillar, nano holes, different material, and showing how the absorption can be increased compared to straight without using them. There's another paper we are publishing in maybe this month. It's accepted, Journal of Optical Society of America, using of similar nanoparticle, but this case we are looking at a perovskite solar cell. And we have a new Marie Curie fellowship, just started a few months back, and we are looking at a different solar cell design and how to improve it. But will that solve the problem completely? No. The reason is solar power is not available 24 hours and 7 days a week. So we need to store it at the daytime or in summer when we have more solar energy. But at night, we need to use, in the winter, you need to use that. But you don't get it. You don't get solar cell in the night. So what you have to do? You have to store the electricity. How can you store it? Simple thing may come lead acid battery. Or tomorrow, Dr. Ismail will talk about the lithium ion battery. So you can try to develop as good battery as possible so that not only that efficient, but also they're cost effective, And also another thing you have to think, if a lead acid battery or lithium ion battery is every day charging, every night discharging, how long it will last? But there are people thinking of other technology. There is a concept of flywheel. It looks strange, but in a flywheel, you can store your energy when you have electricity. So you have a flywheel, which was a zero rotation speed, increase the speed, you use the electricity. In the night, you use the flywheel, this momentum to reconvert back to electricity. And there can be hydroelectricity. In the daytime, you use the electricity, pump the water up the dam, so the water will be more stored. In the night, you release the water to make electricity. There's another people are working on PCM, phase change material. Phase change material has a large latent heat. When you change from one state to another, you need a lot of energy. When you reverse, you get the energy back. A group is working on phase change material. But another thing is also coming is a hydrogen technology. So I will talk a little bit on what is hydrogen technology. Hydrogen is one of the best fuel. You can burn methane, you can burn ethane, but if you can burn hydrogen, is per weight, it is one of the best energy source. So it can be used as a fuel instead of coal, natural gas, or oil. But it needs to be generated. You have to generate it, you have to store them, you have to deliver it from one place to another. You have to use it safely, you have to generate it. Safety is important. So you can generate the hydrogen by burning fossil fuel. But when you're burning fossil fuel, remember you are producing carbon dioxide. But once you got the hydrogen, this is clean energy hydrogen. But you have used a dirty fuel to generate it. You may use thermomechanical process to do that. And many group is working how to make it efficient. So it's not exactly the best answer. That's what we call gray hydrogen. But if you use electricity and split the water and generate hydrogen, that's called blue hydrogen, which is better than gray hydrogen. However, if the electricity was renewable electricity, that is from windmill, wind energy, or solar energy, and if you use that electricity to produce hydrogen, that is called green hydrogen. So our aim is to have as much as green hydrogen as possible. So best will be solar cell, generate the electricity in the daytime when it is a lot in a daytime, and then you generate hydrogen. And that can be used, that electricity can be used 24/7, 24 hours, 7 days. We can use hydrogen as a fuel in industry. We can use hydrogen as a fuel for central heating, for other cooker. You can also use hydrogen to run vehicles. The car, the ship, the plane can run it. You just have to convert how you burn the hydrogen compared to other gases. And I'm aware that IRSN, as Ahmed told, we had worked on a bit on the European project, but unfortunately it was not submitted. That's a separate sad story, however. And IRC is working on not only the solar energy, as Dr. Iken has talked about that, but also they are working on hydrogen generation, and they're also working on hydrogen storage. So it is expected that by 2050, hydrogen will be 24% of all the fuel. That means you just think about how much is the oil gas. So it is a major fuel by 2050. And the fuel market itself will be $500 billion. And the hydrogen economy will employ 1 million people. So that's the thing. And remember, it's another 30 years. And we are all many tech people with a chemical engineer, chemist, physicist, many people are working on the hydrogen economy. But mix of hydrogen air is inflammable, particularly in a 4% to 70%, that area. It can be explosive. So we need to develop sensor to detect hydrogen. One of the best sensor for detection of hydrogen has always been palladium. In palladium, as it absorbs the hydrogen, it expands the volume, it changes the density, it changes the refractive index, both real and imaginary part, it changes the stress. However, the metal oxide based detection, it is slightly unsafe because it can cause the explosion if there is this little spark. So lots of groups are working to use the optical center to detect hydrogen. They're using palladium, again, is one of the best, but looking palladium-based nanoparticle, palladium alloy, because there are hysteresis issue, there are life issues are there, so lots of groups are working on that. And one of the issues we are looking at is that you're looking at a excitation of surface acoustic wave, and that can change its velocity when there is a presence of hydrogen. So that is a project we are trying to develop. So now let's look at the, again, sustainable development goal. We talked about the clean, affordable energy. There is a SDG 6 is clean water and sanitation. One is a good health. One is a climate action. So this is the area, some of them, as I said, we are working new area, but there is enormous potential we have. So the global warming, we need to generate zero carbon renewable energy. We need to generate it, but also we are consuming too much energy. So we need to reduce the energy consumption. So Horizon to this Europe call, as I said, 100 billion euro. The objective of all photonics is not only you have to have a better photonic devices, better system to have a higher data rate, but all the system that requirement of all the call is that not only they have better optical devices from the speed, but they must consume less power. And if you cannot show your research, your future product will not consume less power than earlier, it won't be supported. Because we are very, very serious, everybody, European Union, that energy consumption by all these equipments. So let's look at the energy consumption. Consumed in the industry, transport, residential, commercial, agriculture, many other areas, but also looking at the sector-wise. One of the sectors is illumination. From the invention of Thomas Edison, you can see that incandescent bulb, but it is the most common, but most less energy efficient. And in Europe, it has been banned. You cannot buy an incandescent bulb above a certain wattage unless very specialized. So people move to the fluorescent bulb, but LED is the future. LED is much more efficient than all of them and also lasts longer. This is a simple thing saying that how the lifespan of LED can be 50 times higher than incandescent. Energy uses can be much, much less. So overall, if you replace all the lights at your home, in your office, in the industry, you will save lots of energy and you will contribute to fight the global warming. Another thing suddenly you can say that global consumption of electricity in ICT. 20 years back, 30 years back, you might have a PC at home. Today, you will have a more powerful PC. It is consuming more power. But you also have more mobile phones, cell phones in your home. And the power consumption by the ICT, information technology communication sector, is increasing rapidly. One of them is showing by the brown one is data center. Data centers are consuming enormous amount of electricity. They just want to provide you the service, the Google, and the Google data center, there are thousands of PC, they're connected, and they're providing the data. And they're consuming the energy equivalent to a small town. As example, the Google Kava and Heather data center, in 2015, the energy consumption was 5.7 terawatt hour. So data center needs it, but we need data center. Can you reduce the power consumption by data center? Where the power is consumed? And most of the power is consumed in a data center is transferring data from one memory to one storage to another storage. And these are being transferred, particularly in a data center, in a thin gold wire. And 50% of the power consumed in transferring data from CPU to memory, for fine gold wire. Can we replace it? But if you see that was 2015, 2019, it is 3% of the whole world consumption was data center. 2030, it will increase nearly 10 times. And as I mentioned, most of the power consumption in the data transfer. So what the Photonics working, there are many groups that are working to connect the computer rack to rack, by optical fiber, chip to chip. And when you come to intra-chip, you can use silicon chip using electronics and putting optical component on the same chip. And silicon photonics is one of the best technology for that. So again, photonics is working to reduce your power consumption. Major Horizon Europe research are working on that. So as I mentioned, that optical fiber is used to rack, silicon nanowire is using for intra-chip. And the future is to consider the electronics and photonics on the same silicon chip. And lots of groups are working on it. You also need data for the switching. You need to change from zeros to one or from line A to B for switching. So you need the energy to switch the state from one to another, but also often you need energy to hold that state. And most of the time system is holding this to that particular state longer than the time you need it for switching. So for the holding state, if I can use non-volatile material, then your energy consumption will be less. And there are lots of people now working on called phase change material. So that we only use the energy when you're switching, but when it is a particular state, you don't need any more energy for holding that state. Phase change material has been used for GST and other for the data storage, and people are now working on a network switching. We had a project with Shanghai Jiao Tong University on GST material. It was funded by the Royal Society. And City University is strong in simulation, but Shanghai Jiao Tong had the fabrication facilities. So we designed something, they fabricated, and these are the design and fabricating it. And some of them we published in a very good journal like a Science Bulletin, SES Photonics. So we are working on that. Another area we are working a bit on sensor. So we're focusing on SD6, which is the water quality. Now, every water, you have the arsenic and other material, lead, chromium, all of the things. Water will have pathogen. Another thing is that we are using lots of antibiotics unnecessarily. As the antibiotics now, our residual antibiotics going to water, that is making the bacteria's resistance to that antibiotics. So there's a big initiative in Europe to fight antimicrobial resistance. So what we need a sensor to detect antibiotics in wastewater. We are using insecticide, pesticide for our farm to feed the billions of people, pesticide, and these insecticide, pesticides are going to the water. Number one, we're using more, but also remember, because of global warming, there is suddenly heavy rain. And if there's a heavy rain, there is a run of water. Because your canal cannot carry that number of water because suddenly there's a heavy rain. Lots of rain happen in 1 hour. And then all this insecticide, pesticides, fertilizers, they're going in the water. And if the water has now lots of fertilizers, and also the temperature is a bit high because of global warming, it is causing algal bloom. And algal bloom is killing the other animals, other aquatic animals, and also releasing the toxin, some of them. Europe has lots of projects to detect some of them. There is a specific call to detect mobile pollutants like PFS. There are several calls out there. So simple basic sensor. A basic sensor is that you have a light source. It can be laser, LED. You have a waveguide. You have a sensor area, and that can sense biological, physical, chemical thing, and then you analyze, process this. But basic physics can be simple. The sample can reflect some light. Sample can refract some light. Sample can absorb, so that transmission will depend on how much is absorbed. Sample can scatter. Sample can re-emit to another wavelength. And by detecting these different examples, we can design different sort of sensors. So they can be designed on evanescent, plasmonic, evanescent coupling, bright gating, long period gating, lots of areas of working. I'll just show simple examples. One was very popular in 80s, was side polished fiber, putting a little metal cladding, so that's called evanescent plasmonic mode. Another one is particularly very attractive in integrated photonics. It's called Mach-Zehnder. Although in fiber also you can have some sort of Mach-Zehnder based structure. So you have light, split them. One is reference arm, one is sensing arm. If something is present, what it changes is the phase. So here you try to detect the phase difference. Then you have a Bragg grating. A Bragg grating is a fiber. We have a grating. A light is incident. As a light is incident, a part is reflected, a part, so the transmission part, there's a small part will be left. That reflection one is critically depends on the Bragg wavelength. Now, if this Bragg wavelength can be changed with the sensing, what you want to sense, you got a very attractive sensor. And this sensor has been used very well for strain, stress, and temperature sensing. But for surface sensing, because the mode doesn't come to above the cladding, so sometimes you have to etch the fiber Bragg grating. Then you have the different ways. I'll come to this that you have to sense. So quite often for biosensing, you have to etch the fiber Bragg grating. Long periodic grating has one advantage that the cladding mode extends to the cladding. That's why it's a cladding mode. And if anything presents near the cladding area, you can sense it. You can functionalize this. And that's why it is structurally more stable than the etched fiber Bragg grating. So now, whatever be the technology, whether it's a nanowire, slot waveguide, fiber, if suppose something is there, we need to present it, to detect it, but it has to be selective. In a water, there are thousands of different dirts and pollutants are there. If your sensor is for detecting of arsenic, it should not react with the detection of palladium or chromium. So what you have, if you have a lots of things in the water, they can, normal case, they can deposit on the waveguide. It can change the optical waveguide properties, but it is not selective enough. For selective enough, okay, I think I might have missed that slide. For selective enough, you have to have some sort of layer which is specifically selective for that one you want to sense. Very nice sensor people are designing with called ring resonator. If a sensor, something deposits on the ring, immediately the resonating wavelength shifts. By measuring the shift of the wavelength, you can see that whether something is present or not. So you need to design a very sensitive sensor, but it has to be also selective. And the more exciting is that instead of simple ring resonator, if you have a ring resonator with the slot waveguide, where the light is confined in the slot region, we have shown that lots of work we have done on slot waveguide, then you can have even next generation of sensor. We did some work on long periodic grating. There's a different period. This one is more sensitive. We formed this fiber grating with the graphene oxide coated, selected, and it is a NERC funded a £500,000 project with India, and we fabricated it, and we shown the results for that. I think. So another climate challenge is the heavy rain. In Malaysia, we have a project with Malaysia. They often have a landslide after heavy rain. So what we are working on development of optical sensor to detect the pore pressure in the soil after heavy rain, and also development of inclinometer to detect the land movement. And we have, like in this particular case, in this inside, there are 3 sensors are there, and they are fabricated by 3D printing. This is a project funded by the British Council, and we have also some patent application and some papers on that. Photonics for healthcare is a big area. Our work is negligible, but there are lots of groups. And if you see that most of the optical diagnosis, quite often, they're optical based. ELISA, PCR, many of them are using optical technology. We have a very small project funded by Marie Curie Fellowship. We are trying to develop metal oxide based optical center to detect ethane in your breathing. If you have a diabetes, then diabetic patient has a more ethane in the breathing, and we are trying to detect the amount of ethane in your breath, and that can be used for a screening of diabetic patients. We are just a recent work. We have just submitted a project in this horizon. I think this Friday we submitted it. It is particularly intense light sound interaction. It is a project by major EU industries and universities together. And what we're looking is that SBS, the light sound interaction, slot waveguide with gratings. And these are the innovative one. And this is the acoustic wave in the slot. And what we're looking at that, some of you, if you have worked on a SBS, the SBS, whenever we taught our students earlier, always we said there is a relation between electrorestriction that causes SBS. But there is another thing is saying radiation pressure. And this one becoming dominant when the waveguides are nano size. In a strip waveguide, if you see the red one, is the radiation pressure is lower than the electrorestriction. But in a nanowire, this particularly the slot waveguide, you can see the radiation pressure is higher than the electrorestriction. So if you have a exotic new generation of photonic devices, you want to exploit the SBS gain, you have to consider radiation pressure besides electrorestriction. So the project we have submitted, we want to design a SBS laser with a narrow line width. You want to use for microwave photonics for 5G, 6G, photonics, COM generation, and also sensor. And one work will be on a hydrogen sensor. So the photonics can do for us, it can support the rapid data demanded by 5G, future 6G, IoT, increase the data rate by space division multiplexing, mode division multiplexing, use more and more rack-to-rack, chip-to-chip data transfer by photonics, combine photonics and electronics on the same chip, support lower power consumption by having a much better LED, and replace all the other light by LED. Reduce the global warming by use of better solar cell, more efficient, lower price, flexible, so that more and more people can use it, and it using the photonics for healthcare, industrial, and consumer products. That conclusion, I said that for City University, I've been working for more than 40 years on this area. We have one of the strongest research groups in the world on photonics modeling. But today, I didn't show any of the methods. I didn't show any of our results on that sense, but only wanted to show that how photonics can help everyone to achieve a part of sustainable development goal. Thanks to Ahmed for giving me the opportunity to talk to you today.
Okay, thank you, Professor Aziz. I expect from you such amazing and important topic. Thank you very much and congratulations. I see how from your talk we can get a lot of syllabus to develop photonic, solar, and also relationship to the environment and sustainable development and climate change, etc. This is amazing, and I think we can inspiration from your talk will be very important. I hope in the future we can have a cooperation with London University, because it's a very important one, and especially your group, where you are one of the most important group. And by the way, you are in terms of modulation and modeling and simulation, you are one of the best. And it's not just by chance we make together your talk with the talk of Professor Ben Youssef, and then afterward another talk, a huge talk from Purdue University about computing, quantum computer. So all these stuff are coming together. So I will lead for some questions I will lead the panel to the public, and I will give the word to Ustad Omar, Salim Omar. Are you there?
Yes, I am there.
So please, you can continue.
Yeah. Now, okay, please. Waiting for the raising hands, but there are some questions comes from Mr. Ayub Bouhteb. Question talking about the pollution and the global warming. Did industries around the world use the electrostatic filters to reduce the air pollution? This is his question.
Yeah, I'm not expert on other areas. Even in photonics, it's such a big area. It's a small area I work. So because this is a question of electrostatic and ER filter, but obviously I know that optical sensor can detect the pollution, and particularly the method people use is more called a spectroscopic method. So I know that like a sensing of pollution is an important area, but then question is that once you sense, how to remove it? Yes, there are lots of filters that people are looking at it. Some of the filters people are thinking from lots of nanostructures. Sometimes people are looking from something you can do from natural material. Beyond that, I don't know much about your questions.
Okay, thank you, Prof. Aziz. There is a raising hand from Saleh. Dr. Saleh, please welcome.
He has to open his. Yes.
Okay. He can open. Yes, please go ahead.
Thank you very much, Professor Aziz Rahman. It's a pleasure to listen to your talk and to learn about new technologies related particularly to sensing renewable energy in general. So actually, I have a curiosity here. I saw a beautiful slide where you shared with us about, let's say, radiation pressure on a material.
Yep.
So I'm really confused here because sometimes materials, when you submit, let's say, electromagnetic radiations are absorbed. So what is the meaning, Prof, of radiation pressure? And what is the impact on the structure of the material itself?
Yeah,
Thank
so
you.
so what happens that if you look at the stimulated Brownian scattering, there's an interplay between electrorestriction, a electric field. It changes the electrorestriction means electric field changes the length or dimension. That's why there's a piezoelectric effect. And that's interplay produces SBS, the Brownian gain. But what people also realize that most of the fiber and other, like a fiber, you have a SBS, but fiber dimension is about 10 micron diameter. But when you have a nanoscale waveguide, your waveguide is 200, 300 nanometer, then the radiation, what happens, the radiation also, it works like a force. And it changes deform the side of the structures. And that interacts also with the SBS. So what people are showing that very small dimension, the effect of the radiation pressure, the electromagnetic field there, because remember, is a very small dimension now. That density effect is much more higher than the electrorestriction concept people use. Electrorestriction is also there. So you can see there are some papers on called radiation pressure in SBS. There are quite few work is there from, I think, Yale University, particularly. They did lots of work, some from France. I think that's no, from Switzerland, there's some group. And what we did the modeling of that for one structure. So if it is a simple optical fiber, radiation pressure is not that important, it's weak force. But if it's a very narrow optical waveguide where you want to exploit light and sound interaction, you should not ignore radiation pressure because that is being the dominant.
Thank you very much, Prof. Thank you very much.
Any other questions from the participants? There is one. Thank you. Okay, so that's it.
I have one question.
Yes, go ahead. Go ahead, Prof. Okay.
Professor Aziz, you know, actually everybody is talking about smart city. And sensors are very important. So it will be a big market if we move to smart city everywhere. So do you think it's a niche now, or really it's a big stuff to work on it? And if the government, for example, in England, they give a lot of money to work on research and development in terms of sensors for smart city, for example.
Yeah, one advantage of optical sensor is that, because as you know, that optical fiber is the minimum loss. So what you can have a 20 optical sensor in a road, one road, another road, but going through the same single optical fiber. It is sensing 20 different places, 1 kilometer apart. But you need only one interrogator, because as long as your fiber getting, each of the resonant frequency wavelength is different, the same optical fiber can interrogate. So what you call is a multiplexing. You can do whereas if you have other sensor, you cannot multiplex it. Each sensor is separate. You have to run 20 different cables, and you have to have a 20 different interrogator. But optical sensor can be multiplexed, can be distributed, and that's why the big advantage will come from optical sensor.
Okay, thank you very much. Thank you. So Dr. Ustad Salim.
No question now. So maybe within the coming days also, we will still receive the questions, and we can send it to Prof. Aziz, inshallah, Aziz Rahman, and we will continue to the end of 30th of October. So thanks, Prof. Aziz, and the floor to you, Dr. Prof. Ahmed, please.
Yes, thank you very much, and I hope we will invite you sometime to our virtual university to help us to give talks as a webinar, and I hope that we can produce some good student to send it to University of London in the future, that they can make their PhD in your department. I hope.
Yeah, thanks. It will be great to have like an interaction, because I have PhD students who finished with me from Nigeria, Ghana, and other part of the Africa. We'll be happy to have a very good student from there, but also there are European Union, sometimes research call. If it's involved with Africa, we can look at it, because we know that through your research institute, there are lots of areas we can collaborate, and that will be important.
Yes.
And I've never been to Morocco. If there's any time the COVID gets better, situation gets better, it will be my pleasure to go and meet many of you personally.
You are in pipeline. You will come. I'm sure that we will do it. I think I hope in December we have a conference on power to X, to hydrogen, and we will see if we can manage that you come and you give a talk. I think thank you very much.